Thanks very much for the introduction, and thanks very much, Robert, to speak here. It's a happy coincidence that we can have the meeting online, on site. It makes it different. I have 2 weeks ago I gave the first seminar in 2 years that was on site, and it is different than doing it online. I think we can have more of a conversation, and I'm happy to take any questions that you have on the way. If there is something, please jump in. So the title of the talk is Behavioral and Experimental Macroeconomics and Policy Analysis, a Complex Systems Approach. I should say, so I have done this research for a long time at the University of Amsterdam. I did a PhD at Groningen University, but I've worked at the University of Amsterdam for a long time, and more recently in the past few years I've been associated with the Bank of Canada, where we try to apply complex systems models, behavioral models, to policy analysis. So that shows also that institutions have an interest in this kind of research, but I should always make this disclaimer. These are not the views of the bank, these are my views. So you cannot blame the bank. This is a survey paper in the Journal of Economic Literature that appeared last year. It's a long survey. I don't have time to go into all the details, but I will discuss some highlights. What I believe are some highlights of the paper. Now it should move forward. There it is. So for this audience, for this complex systems group, it's very nice that the University of Utrecht invests in complex systems and has a group, has people sitting together in a very nice building and discuss complexity problem from a disciplinary perspective. That's great. Here are some applications of complex systems. I don't have to explain it to you, I think, but financial markets and economy and depressions and booms and busts are two phenomena that I can also be described with complex systems, and there's a lot of work going on in that area. So again, I don't have to go into details what is a complex system for this group, but here are 3 bullet points that are important to me and to economics. The first characteristic is the interaction of heterogeneous agents at the micro level. That's the micro behavior, and that micro behavior creates patterns and structure at the aggregate level. Okay, and those are the emergent macro behavior that we are interested in. And a system more is different. A system with many agents is very different than a system with a representative agent, for example. Now, of course, complex systems. I don't know why this is happening.
The people online can't see the people online can't see the slides as well. Jenny, you're an Apple first. Can you see my lineup? Has this changed?
No, no. Probably have to reshare it.
Reshare.
I want to give it a shot. So maybe I can share. This one. No.
Yeah.
Okay. Sorry about that. Technical problems.
Yeah. Okay, the second characteristic feature is nonlinearity and the phenomenon of critical transitions, where, for example, for economic applications, you can have situations where you have two long-run steady states, one good equilibrium and one bad equilibrium, and you can have critical transitions between those equilibrium. And these critical transitions can be large and they can also be irreversible. It can be very difficult to get the system back from one equilibrium to the other. Now, the third characteristic is important for economics. Namely, complex systems in economics, they have an important difference with complex systems in physics. Namely, in economics, you could say that particles can think. The agents learn and adapt their behavior over time. Okay, so agents have expectations and beliefs, and they learn and adapt their expectations over time. That's a very important aspect for economics. And traditionally, expectations are modeled in economics as rational expectations. Okay, but that's a very strong assumption. Rational expectation means that agents know everything, understand all the details of the model, and make the best possible forecast conditional on their knowledge of the model. Okay, in a complex system model in economics, we need a theory of expectations. We need a theory of the mind, a theory of adaptation and learning, and that is very important, and that is also a challenge. How do you model irrationality? Because Bob Lucas, a famous Nobel Prize winner from Chicago, famous economist who introduced rational expectations, said there's only one way you can be right, and that's to have rational expectations, but there are many ways that you can be wrong. And if you make assumptions in a model that agents are wrong, then how wrong are they? What are the mistakes they are making? And what is a realistic theory of non-rational expectations? So that's an important challenge. And how do you model expectations in a complex environment? That's the main theme of that survey that I mentioned. And the idea here of the behavioral theory in the models I'm talking about is that agents use simple heuristics, but they try to do smart heuristics, sort of optimal, simple heuristics. So within a simple class of heuristics, they try to find the optimal strategy within this class of heuristics. That's in general the kind of theory of expectation we're considering.
Maybe just clicking the slide. No?
Yeah, that works. Okay, so that's the main focus of the survey, boundedly rational expectations in stylized complex systems. And as I said, the paper is long, so I chose 4 topics that I want to discuss here. In fact, 3, because the first one, simple forecasting heuristics that make us smart. The very first one is just a simple AL1 rule. An AL1 rule with one leg. Now that rule has 2 parameters, a constant and an autocorrelation coefficient. Okay, and agents can try to find the optimal AL1 rule. And that kind of a theory of learning, and then they change their AL1 rule, they change their parameters over time as more and more observations become available. They re-estimate their AL1 model. Now that's a very simple way of doing an AL1, and it's nice in the sense that this AL1 rule is called the behavioral learning equilibrium when the parameters satisfy 2 conditions. The first constant parameter has to be equal to the sample mean of the process. They learn the sample mean, and the second parameter learns the autocorrelation coefficient of the process. So if the agent finds the optimal AL1 rule, then the sample mean is correct and the first order persistence is correct. And that's already a nice theory of learning that we are now also applying in the models of the Bank of Canada, and see how policy behaves under this kind of learning of an optimal AL1. So that's my first example. A simple AL1, and you get much richer dynamics than under rational expectations. You get very persistent behavior. You get amplification of shocks. So it's a very rich learning environment when all agents learn the optimal AL1. But here I want to talk more about heterogeneous rules. So I'm going to give you a model of heterogeneous rules with anchor and adjustment rules. Okay, and so that's a model I will discuss. And what about empirical validation? That's my next point. Empirical validation of expectations you can do with laboratory experiments. So I want to discuss some laboratory experiments and talk about what we can learn from laboratory experiments on expectation formation. And then the relevance for policy. How can you manage complex economic systems? How can you stabilize complex economic systems? And although I talk about very simple and stylized systems, and I'm not claiming that they are perfectly, that they are a perfect fit or perfectly the right model, but we do get some important insights for policy, how to manage a complex system in terms of positive feedback and negative feedback. So that will be my last point that I will make.
Because may I ask, what is the motivation for this AL1 rule? Because normally that's sort of, you have a damping and you have a noise, right? Added noise. Is that motivated from that, or is it compromise?
Yeah, well, it's a compromise between simplicity of the rule and complexity. And the nice thing about when you have the AL1 rule that is optimal, you have actually fixed your two parameters, and that is a model that is parameter free. And that's nice. So you don't use extra parameters for your expectations and something. So that's nice. Whether or not AL1 is enough is another question. So AL1 means that you have the average mean reversion to the equilibrium. You have that correct by your AL1 parameter. Okay, the average mean reversion is correct. Now, it could be that in some markets, housing markets, financial markets, you have more oscillatory behavior. And then you would like to have not an AL1, but an AL2 rule that can be a trend extrapolating rule, as we will see. And if that aspect is important, for example, in housing markets, AL1 might not be enough. You could do an AL2, you add a third parameter, and you learn the third parameter over time. But the hope is that with a relatively simple rule, you can match the data. That's the hope. And actually, this also is at the heart of the lab experiments that we started running in Amsterdam now 25 years ago, because when I was talking about AL1 rules then, and theoretical audience, part of it, they would say this AL1 is too simple, and another part would say it's too complex, it's too rational, too much to ask for a large population in the economy. So AL1 is a sort of compromise, simple compromise. Lab experiments with human subjects. So why would you run macro experiments? Why are they important? Well, if a theory does not work in the lab, why would it work in reality? So if you have a theory, you can get some useful insights by testing it in the lab. Now, what is a macro experiment? A macro experiment, we are interested in group behavior. So we have subjects in the lab, a group of subjects, and we are interested in the group behavior. Of course, the group behavior depends on the individual behavior, the micro behavior. So you have micro behavior and you have macro behavior. And in the lab, in a controlled lab with human subjects, you can control the environment and you can study the micro data, you can study the macro data and find the connection between them. So that's macro experiment. And the experiments that I will talk about are so-called learning to forecast experiments. Basically, we program an economic model with expectations. Everything is according to the theory of the model, except the forecasting behavior in the economy, the expectations in the economy. They are done by the real subjects. And the subjects are paid by how well or bad they forecast. The better they forecast, the higher they earn. So those are learning to forecast experiment, and that's putting an expectation feedback system in the lab. And then if you have such a system, you ask yourself, on what do agents coordinate? Maybe they coordinate on the rational equilibrium. Maybe not. Maybe on something else. Maybe on some kind of behavioral equilibrium, or maybe on boom-bust cycle patterns. Okay, and that you can study in the lab. This is some motivation by Lucas, but let me, because of time, skip these economists. You can read it on the slide how it relates to some statements of famous economists. So I mentioned the feedback, and the feedback of the system is very important for the outcome of the dynamics. And I want to show you two systems: a linear system where the price is a function of the average forecast of 6 subjects in the lab. Okay, and it's a negative feedback system. There's a minus sign here. When the average forecast goes up, the realized price goes down. And this comes from a simple, very simple model in economics, the so-called cobweb model, the Hawke cycle model, where the producers form expectations. And when it's producer driven, when they are more optimistic, they produce more, the price goes down. So that's the negative feedback. Mathematically, that's the negative sign over here. Okay, so this is epsilon t is a small noise term, and 60 is the equilibrium. 60 is the rational equilibrium. When everybody forecasts 60, this completely drops out, and you get 60 plus small noise. So 60 is a self-fulfilling equilibrium. It's the rational expectations equilibrium. Okay. Now, we have a second treatment where the minus sign becomes a plus. And then you have positive feedback. And that's positive feedback is important in many financial macro systems. But for example, a financial system with speculation that are demand driven. When the expectation of the investors go up, they become more optimistic, they demand more stocks, they buy more stocks, price goes up. Okay, that's the positive feedback. If the average forecast goes up, the price goes up. Okay, now this system has the same equilibrium, 60. 60 is the rational expectations equilibrium of both systems. So under rational expectations, they are exactly the same. We have the same equilibrium, 60. And the only difference in these two systems is the slope of the linear map. That is plus 0.95. It's here like a sort of discount factor. It's a number close to 1. 0.95, and here it's minus 0.95. Okay, now for example, under naive expectations, when everybody expects the previous price to continue, so you plug in a PT minus 1 here for everybody, then you have a linear system with eigenvalue minus 0.95 that is stable under naive expectation. And this one is also stable with an eigenvalue of plus 0.95. Okay, so both systems would be stable under naive expectation. So that's a simple model of expectation that makes the system stable. But will they be stable in the lab? Well, here are the feedback, linear feedback maps. Negative feedback, just a line, the red curve with a slope minus 0.95. And under positive feedback, a positive slope plus 0.95. And now maybe you observe a difference that here the equilibrium is very visible, right in the middle. That's the equilibrium. Maybe agents should be able to learn that equilibrium, but here also the equilibrium is unique. It's in the middle, but the red line is very close to diagonal. Okay. In fact, if the slope of the red line would be plus 1 rather than 0.95, it would coincide with the diagonal, and you would have a continuum of equilibrium. Okay, so in systems with positive feedback, strong positive feedback, with an eigenvalue close to 1, you are close to the situation of a continuum of equilibrium. Okay, and the question is in the lab, would it make a difference if you put these systems in the lab? Would it make a difference? Yes. On the left, you see the negative feedback, the price in the negative feedback market in an experiment with 6 subjects making a forecast, and the price is very stable. The individual forecasts are here, and they converge to rational expectations. So this is nice because we give the students actually rather limited information about, we don't give them the equations of the model, but we tell them a story, a qualitative story about the price rules I showed to you. And we tell them whether the feedback is negative or positive. We explain that to them. And then on the negative, the system is very stable. The forecast coordinates on the rational expectations equilibrium. So you could say the theory of rational expectation works pretty well here. If you ignore the first 5 to 10 periods, the theory works well. Okay, but not on the positive feedback. Here's an example on the positive feedback. And the market fluctuates for 50 periods. You have a sort of boom and bust cycle. And you see the expectations are very strongly coordinated, but not on the rational equilibrium, but on the price here. On the wrong price, you could say. But expectations are very coordinated, very strongly coordinated. And that's already remarkable because subjects do not know the forecast of the others. Yet expectations are very coordinated.
Question. What's going to happen if you have 1 million agents?
That's an expensive experiment. But
On a computer you can do this, so you will still get the same movement bus cycle.
Yeah,
or
on a computer, but if you really want to do it with human subjects, then it's complicated. Of course, you can simulate on a computer.
But I thought the equations that you wrote down in the previous slides, they could, I mean, you could put that in a computer, right? So because all
Yes.
regression models are well handled on a
Yes,
computer.
no, but if you want to, so the group size, I mean, you're raising a very important point. The group size is important. The group size is 6 here, and you can raise the question, what happens for larger group sizes? Now, of course, larger group sizes are more costly. You have to pay these subjects money. They earn €25 in a session of 1.5 hours, something like that. But you would like to run larger groups. We have done a few of those. We have done groups of 25. That sort of fits in the classroom. And we have groups of 100, that is 2 labs together. Okay, and the behavior is similar. The behavior is similar. So I can answer the question until 100, 1 million, but that gives us some reason to believe that also in very large group, the behavior would be robust. But it's an open issue, and also there are other settings maybe where group size could be important, where a small group gives you different results than a large group. And that's interesting, of course, and that can happen, but in these learning to forecast experiment of this type, the behavior is similar. Okay, to give you an idea, on the left, we have the negative feedback, and we have the blue dots are the forecast in the first periods. And the red dot is the price. So the forecasts are here, and because the negative feedback, the price is there. And then in the next periods, this is what happens. So you see a few subjects jump with their expectations in the neighborhood of the last observation. There is also a subject that goes the other way, it goes against the market. And maybe that subject has understood the negative feedback. And maybe it was conscious that this subject goes on the market. Given these forecasts of the blue dots, the red dot is the next price. And then we see in the next here. And you see already in the fourth period, you have a nice situation. You have three are slightly optimistic, 2 are slightly pessimistic, but they are rather close already to the realized price. And the realized price is rather close to the equilibrium of 60. If you look a little bit further, then here after 6-7 periods, the forecasts are very close to the rational equilibrium, and the price is also very close to the rational equilibrium. So it works here. The rational theory is a good theory under this negative feedback.
Have you tried the same with a larger epsilon so that we get just continuous?
No, we have not done that. And the reason why we had a very small epsilon is to slightly perturb. So if everybody sticks to the same forecast, otherwise you would get a constant price. To avoid that, we had a small noise, but we haven't done tested larger noise.
Because here they converge on the rational mean expected price, so the 60.
Yeah.
I'd be interested if there was a consistent spread, if they would also.
You know, if you have noise, if you have the equilibrium is noisy, then expectations are probably also a little bit noisy. It sort of breaks down the coordination, but breaking down the coordination may be stabilizing in this environment, and the price may, in the end up somewhere in the middle, close to the equilibrium. That's what I would expect. Okay, positive feedback. What do we see there? Okay, so here you see the blue dots are the forecast. The red dot here is at 38, is the initial price. And then this happens. You see forecast jump close to the price, and we are pretty close already. And you see, after 3-4 periods, the forecasts are very close to the price. So the forecasts are pretty good. But the price is very different from the rational equilibrium. Okay, so that's what you clearly see. But it's clear that in this kind of markets, where the majority believes in this price, that's a better forecast than making the forecast of 60. Okay, so if we continue this plot, then you see price goes up, and now the price overshoots. It's like it's overshooting, like expectations follow some kind of trend. And this is what you get. Okay, so you get these oscillations, and the forecasts are very close to the realized price, but not to the equilibrium. Okay, so here are 7 groups under negative feedback, and they're all pretty stable. And here are 6 or 7 groups under positive feedback, and they are everywhere. Some of them are fairly stable, like this one, this blue one is fairly stable, oscillates a little bit, but they're also boom and bust cycles. Okay, and so here you have convergence to rational expectations, and here you have what you could describe as coordination on self-fulfilling equilibria, almost self-fulfilling equilibria. Not perfect, but almost self-fulfilling equilibria. Okay, here's a model that we fitted to the data, and I'll show you the model equations in a minute. But the model has 4 strategies, and agents tend to switch to strategies that have performed better in the recent past. So there's a kind of reinforcement learning or evolutionary selection, if you wish. Agents switch gradually to better performing strategy. That's the model. What happens under negative feedback is here the red data points are the experiments, and the green is the simulation model. Okay, you get a nice fit here, and also here the green simulation fits the positive feedback quite nicely. What happens in the strategy space? There are 4 strategies. These are the fractions of the 4 strategies, and the purple one is adaptive expectations. It's just an average of the last forecast and the last price. And that works very well in this negative feedback environment. Agents coordinate on adaptive expectations, and that stabilizes price forecast and prices. Okay, so that's adaptive expectations. Under positive feedback, the blue and the green strategies are better, and those are the trend following strategies. They make a forecast last observation plus a parameter times the last change of the observation. That's a simple trend following rule. The strong trend rule does well in the beginning, then the trend weakens, then the weak trend rule does well, but adaptive expectation does not work at all here. And trend following rules do not work at all here. So under positive feedback, you have trend followers amplifying fluctuations, and that already gives us an idea for policy. If negative feedback is more stable, and strong positive feedback is unstable, then as a policymaker, you can try to weaken the positive feedback. Okay, so add negative feedback to the system to stabilize the trend following behavior. And we're going to see that later on in an example where that works quite nicely. Yeah, these are again negative feedback experiments. Oh, sorry, positive feedback experiment, negative feedback experiment, but this time with a large shock. There's a large shock to the equilibrium price here from, what is it, 57 to 41. And there's another large shock to the equilibrium price from 41 to 63. And under negative feedback, the subjects learn it very quickly. Again, negative feedback converges. But under positive feedback, it's difficult to learn the new equilibrium, and it's very slow. It's very slow. So there are coordination failures on the positive feedback, and there is coordination on rational equilibria on the negative feedback. Let me skip this. So what's the model that we are using? Agents choose from a finite number of simple forecasting heuristics, and they choose according to the performance. The performance is, the learning is performance-based reinforcement learning. They look at the performance of the heuristics and tend to switch to more successful heuristics. How do they do that? Well, we use this discrete choice model. Also, this comes from physics. The Gibbs probabilities have similar expression as e to the power beta times the fitness divided by a normalization factor. But we have a discrete choice model with so-called asynchronous updating. This delta times the previous fraction is the fraction that sticks to their strategy in a given period. They only switch occasionally. Okay, 1 minus delta switches to better performing strategies. And for switching, strategy switching in the lab, you need this delta parameter. It's typically 80%, 90%, which means that in a given period, only 10 to 20% switches. Okay, that's the switching model between strategies. And here are the 4 strategies that I was using in this earlier simulation. There is adaptive expectation with coefficients 2/3 and 1/3. There's a weak trend rule that forecasts the last price plus 0.4 times the last price change. And there's a strong trend rule that has a coefficient 1.3. And these coefficients came from estimations of individual strategies in another experiment. Okay, and we just said, okay, let's take the smallest one, let's take the largest one. But you can play with that coefficient. And then there's a 4th strategy that's also a trend following strategy. It extrapolates the price change with a coefficient 1, but the anchor is different. It's not only the last price, it's the last price for 50%, and the other 50% is given to the sample average of all previous prices. So this is a proxy of the equilibrium of the system. Okay, and this rule has a smarter anchor than the other 2 rules. And here is a fit of the model. Again, the blue points are the experiment, the red is the simulation, and you get a very nice switching model, gets a very nice fit on the positive feedback, also a very nice fit on the negative feedback. And in the strategy space, we look here at the strategy space. The blue one is again the strong trend following rule that dominates the behavior. Adaptive expectation does not that good. The strong trend rule performs much better. And here's interesting, here it's not adaptive expectation that wins, but this is actually a trend rule that wins with negative coefficients. So that's an agent that has a trend that recognizes the negative feedback, the up and down fluctuations in that negative feedback system. And that works best, and that stabilizes the price. Okay, any questions?
Let's say in the bottom image, if you take out the black strategy, just ignore it.
Yes.
Which one would survive, and how different would the prediction be?
The survivor would be mainly the adaptive expectations, and the behavior would be rather similar. The exploitation of the negative coefficient gives you some advantage during the transitions to another equilibrium. Then for a short moment, the price is fluctuate a little bit up and down, and then that strategy makes us different.
But the fit of the adaptive one to human behavior is quite
Yes.
good anyway.
Yeah, it's adapted. I mean, we did many of these experiments. We always estimate individual rules, and in this kind of environment, adaptive expectation is one of the popular rules. It works well under negative feedback, not so well under positive feedback. It depends. Okay. Now let me think. I should talk 45 minutes, right?
Yeah, more frequent.
Roughly. Okay.
I mean, there's questions in between, so I mean, it's flexible.
Yeah. So one thing that you could say, or that people have asked us when we talked about these experiments, oh, that's nice, these coefficients, these rules, but where do you get these coefficients? How do you get these coefficients? Okay, so and that's a fair point. Well, how would subject arrive at those coefficients? So I'm going to show you a genetic algorithm model that learns the coefficients of these rules, and I'm going to fit that GA model also to the same experimental data, and then we will see we get a very nice fit. So I'm after a model with learning of the coefficients, and that's a GA model with, you could say, smart heuristic. This is the general form of the price forecasting heuristics. It's an anchor and adjustment rule. The anchor is the first two terms. The adjustment is just the trend extrapolation. But the trend parameter is now a parameter that is learned by agent I. There are H rules. Each agent has H rules, and H is like 20. And this is in time t. So this is a coefficient that the agents try to learn. The trend coefficient and the alpha coefficient is a weighted average of the last price in the last forecast. So again, this part is adaptive expectations. Okay. Now, and there are two parameters, an anchor and a trend, and agents try to learn this model. And there are all kind of special cases involved here. When alpha is null and beta is null and the forecast is the fundamental, then you are in the rational equilibrium. So that's a special case. When this coefficient is 0, you are in adaptive expectations. Okay. When this coefficient is 1, this drops out and you have a pure trend. So there are special cases within this general GA model setup. What do you get? Okay. GA models are evolutionary selection models. I don't have to discuss it here very much in detail, but there's always a selection of better rules. What is important, the GA models in economics, after reproduction and survival of the fittest and random mutation, we typically also use an election rule, that the rule has to be better than the previous parent rules, otherwise we don't take it. I mean, that's sort of a human element in a market. You want to switch to a rule, but only when it's better than the previous rule. If it's not better, then you ignore it. So that's the election operator that is used in these GAs. Okay, well, and here is the data, lab experiments, and the fit of the model. And I always have to look what are the data and what are the model simulations. The top is the lab experiment, negative feedback and positive feedback, and this is the GA simulation. And you see in the lab the price is very stable, the forecasts are very close to the realized price. You learn the new equilibrium rather quickly, and that also happens under GA learning. You see in the beginning there is some heterogeneity of the rules, but then the GA agents learn the new equilibrium. Also in the positive feedback, in the lab, there's this coordination of subjects forecast on the price, and that's also what the GA agents do. Okay, so this GA model gives a nice fit. That's also shown in this picture. These are 1,000 Monte Carlo simulations of the GA model. Okay, and the blue dots is the confidence band. You see, here the confidence band is very small. The data stay within the confidence band. Then there is the shock. Then there is more variation. Then the confidence interval is very small again, and so on. But the model fits very nicely on the negative feedback and also on the positive feedback experience. And these are simulations that are 65 periods, that's how long the experiment is, 65 periods ahead simulations. So we initialize the GAs by the initial data of the experiment. The first 2-3 periods, those are the initial forecasts and the initial prices. We use that as initialization. Then we predict 65 periods ahead, and then the blue confidence band is the 90% band of the GA model, and it gives a very nice fit. What are the coefficients? Here are the alpha coefficients at the top and the trend coefficients at the bottom. The alpha coefficient at the top and the negative feedback, well, this is the median or the average, and it's close to 0.5. So this is 50% weight to the last price observation and 50% weight to the last price forecast. And the positive feedback, the anchor is not 50-50, the anchor is actually close to 1. It's more like 0.9 to the last observation and only 10% to the last forecast. Okay, so you see a difference on the negative feedback and positive feedback for the anchor and also for the trend parameter at the bottom plots. Here the trend parameter and the negative feedback is basically close to 0. There is no trend, there is no clear trend, that parameter is close to 0. And on the positive feedback, the trend parameter is significantly positive towards the end of the experiment. Okay, and if you look at the optimal rules, then on the negative feedback, it's 50-50. It's an adaptive expectation rule with 50-50 weights. And on the positive feedback, it's a trend following rule with a coefficient of 0.9, trend coefficient, and a lot of weight given to the last observation. Okay, so I hope that I illustrated how you can run these lab experiments, get the data and estimate models on the data, and how you can have simple models of heuristics. And these are the average heuristics in those environments. Yes.
I have a question here, because I know in these experiments, often the participants are also asked to describe a little bit their strategies in the end.
Yes.
I was wondering, when you compare this GA model where you see that agents learn like this and maybe some of the feedback from actual people, how do they compare?
So we almost always have indeed a small questionnaire at the end of the lab experiment, and we ask about their strategy, and so in the hope that we get some answers of what they are using. But it's not easy to translate those answers in an exact mathematical formula. But you do get some students who clearly use a trend following strategy. They use the word trends, sometimes they use the word adaptive expectations. And for a few of them, you can even write down an equation that they have been using. And what you also see is that they may change their strategy from the beginning to after some time, they revise their strategy and maybe they stick to it or they switch again if needed. But you do get some information that is, I would say, consistent broadly with the model, but it doesn't prove that the that model is right. But it's certainly useful information from those surveys at the end. Okay, so how do you, as a policymaker, as a central bank, manage expectations? It's a very big topic again now that inflation is increasing so rapidly. Central banks are very worried about how to manage expectations on inflation and on other variables. How can you manage them? And I mentioned the positive and the negative feedback. Here are some other examples from financial market experiments with bubbles and crashes. Now this is very unstable, large bubbles and crashes. These are the groups of 6, and here are the groups of 25 and 30 that I mentioned. And you see also you have here large bubbles and crashes. And that also, you ask the question, is it the positive feedback that causes this strong instability? Here are some groups of 100. Okay, so here is the group of 6 subjects. So the red curve is the price, and the black lines are the 6 subjects that forecast. This is with a group of 6, and this is with a group of 100. Okay, and you basically, in a large group, you see the same patterns. You see a large bubble and a crash, and expectations coordinate on this large bubble, and then you have a crash. We looked at the individual strategies in these large groups and in the small groups, and we estimated models for the strategies. But we found some differences, but the differences are not statistically significant. So broadly speaking, the large group behavior is similar as the group of 6 for this particular lab experiment. Again, what causes this instability? Is it positive feedback? Okay, well, and that you can actually, again, test in an experiment. You know, that's the nice thing about experiments. You have a theory, you can test it in the lab. And a problem with a theory is you can always write down a theory of expectations. You can always write down a theory of learning. In fact, you give me a model with an equilibrium, and I'll find you a learning algorithm that for that particular model gives stability and convergence to the equilibrium. If you develop a smart theory, you can always do that. So it is important to bring it to the lab and see what happens in the lab. Okay, and this idea of is there a relation between positive feedback and the instability? Well, you can run different treatments with different strength of positive feedback. And that was done for a so-called housing market experiment. This is an asset pricing equation. The price is the discounted value of the price expectation in the next period plus the dividends in the next period. And for this housing model, that's housing rent plus a small noise term. And now this is a standard model. If you don't have this minus C here, this is a standard asset pricing model. The C parameter is housing construction. So now we're going to build extra houses, and mathematically that weakens the positive feedback. The coefficient goes from, the eigenvalue now becomes 1 minus C divided by 1 plus R. So when C increases, the eigenvalue decreases. Okay, that's what we're going to do. So, and here are the results. When there is no housing construction, the eigenvalue is 0.95, as we saw before. And that's like an interest rate of 5%. Okay, and then you have this output. You have these strong bubbles and crashes, bubble crashes that we have seen before. Now you have a different treatment, again with groups of 6, that has an eigenvalue of 0.85. And you see the large bubble disappears. We get oscillations. Not stable yet because the amplitude is sort of constant, almost constant. But you get oscillations. Then an eigenvalue of 0.7. And then you get oscillations and very stable. Okay, so weakening the positive feedback makes the system more stable. And what does the model say? I use the same model, fit the model on the data. The red is a simulation, the blue are the market prices in the lab. Here are the strategies, and here it's the strong trend following strategy, the blue one that dominates the behavior. Okay, here it's the strong trend rule that dominates in the beginning when there is a strong trend, but then does worse. And rule number 4, the learning anchor and adjustment rule, that was the rule with the smarter anchor, gives 50% weight to sample average in the past. Okay, and that does better when the market oscillates, and that takes over. Now, in this case, with an eigenvalue of 0.7, the trend rule does well in the beginning when there's a trend. Then the trend switches, and the trend rule does poorly in predicting that switch, that trend reversal. But rule number 4 is better in predicting trend reversals. and starts dominating the market. And then until the end, until period 35, adaptive expectation was the worst rule till then, but then becomes better and takes over and stabilizes the prices. When adaptive expectation dominates, we stabilize the price. Okay, this is what I wanted to say. Here are my conclusions. If it works. So I think complex systems are very important for economics as well as for other applications, but also I think for economics it's very important. We have seen a parsimonious heterogeneous expectation switching model that fits the lab experiments well. And also, I didn't show that, but we have also estimated these kind of models on housing prices, for example, on stock market data, and there it also works. And for policy, adding negative feedback to the system or weakening the positive feedback makes the system more stable. And that's, of course, that's a sort of mathematical, abstract mathematical statement in terms of a model, what you can do to stabilize expectation dynamics. I should stop now. There are maybe still a few minutes left for some questions.
It's very clear. Nice. So, questions? Maybe Jason first?
Yeah, so I was actually kind of curious about the empirical data. So I was wondering what degree you have data about individual behavior that you can use for empirical.
Yeah, well, that we didn't go that far. We didn't look at individual data. That would be great through an agent-based model and based on individual data. I mean, we're doing some work on agent-based models as well, but not in the housing pricing context. But when I refer to the housing price model, we do have a model of heterogeneous expectations and switching between two rules. One rule is mean reverting, and the other rule is mean extrapolating. Okay, and that we use aggregate data of housing prices to estimate that kind of two-type switching model. And here are some results. These are US data. This is Japan, and that's the Netherlands. This is based on joint work with Wilco Bolt and Mario De Metzis from the Nederlandse Bank, the Dutch Central Bank. This first plot is the deviation from the fundamental. So we have a notion of fundamental based on interest rates and growth expectations. That's a benchmark fundamental, and these are the deviations from the fundamental, these are the fractions of mean reverters. So they believe in stability of the market, and you see the fractions, they vary a lot. And this is basically, again, it's an AL1 model, but the coefficient of the AL1 changes over time and depends on the fractions of the two strategies in the market. So it's a time varying AL1 model is time varying parameters. And this plot shows when that AL1 coefficient is below 1, this horizontal line is 1, or above 1. And when it's above 1, you could say there's a bubble. And here are 10 years in the late 90s, early 2000s in the US data where you had this bubble state. And you see that I have been other periods, and this is very robust. Other countries, we've done this for many countries, and you get typically the same behavior in Japan, who were on a negative bubble or who are still on a negative bubble, and also in the Netherlands there have been bubbles. So switching behavior also seems to be relevant in housing markets.
Yeah, so if I'm not mistaken, this regressive one model is probably a dynamical system model with one-step memory. Is that correct? That it retains or remembers one step behind. And what would happen in that case, if this is my correct understanding, then what would happen if the agents remember more?
Yes, first of all, mathematically, this model is an AL1 model with what is a time varying coefficient. And the time variation depends on the lag state variable and 2 lags and 3 lags. And those lags come in because it's based on the performance of the strategies. So you have 3 lags in total. In the forecasting rules in this model, agents only use the last observation, so only 1 lag. And you are right, you could extend that to more lags. We haven't really tried that, but I would expect mathematically to get in the simulation similar behavior. What may become more difficult is to estimate the coefficients on the higher order lags because, and I'm not sure whether they are statistically significant. I mean, that could be an issue. When you have fewer lags, then you can easier obtain a statistical significance. But I mean, in reality, of course, history matters. We all know that, and that can be built into these models if you want.
Any other questions? There's one about your last remark about the negative feedback, right? Which sort of governments or banks have to introduce. So
Yeah.
they could do it in one element here, but then it would have a lot of other effects, right? Is that
Yes.
is that sort of this total connection? Is that considered?
Yeah, that requires basically I think requires a whole research program to handle all these different cases and these different assumptions. You can make many assumptions in a lab experiment, and these are very few and very stylized. And in a lab experiment, it helps if you have a clear focus. So if you have only the only degree of freedom here is basically expectations, but there are of course other things that are important in the economy. And you can set up new experiments to do that, and you can also try to build a realistic, between quotes, economy in the lab, and then see what happens in the lab. But I mean, I think in macroeconomics, lab experiments are relatively new. It is becoming more and more accepted as a complementary research methodology, but it's still in its initial stages, and a lot of work can be done.
Okay. Any other final question? If not, oh yeah, it's all online. Yes, is it
It's
online?
not online.
Oh,
Do you want to present this?
oh, okay, yeah. Well, let's thank Kars again. Present.
Thank you.
It's nice for evening.
Ah,
Evening drinks.
okay. They will be happy when I bring this home.
No trouble.
Thank you.
And on
So-
Thursday we have the president of the Santa Fe Institute, David Greco, online. So you're welcome here to join us, and we'll watch it together. So
Yeah, and I can promise you it will be a spectacular talk. I mean, I heard a talk from him in Cornell University a year ago, and it's a fantastic speaker. It's good probably to him.
I haven't met him.
Yeah, but yeah, it will be fantastic. So you're all invited to talk. Okay, thank you.
Okay.